greatest day of your life / tomorrow / Thursday's pretty damn good too. What are we going to learn? The fundamental theorem of calculus. Did anyone bring any food?
Yeah.
What did you bring?
I brought brownies and Madeleines.
Whoa. Okay, good. Sort of like prepare them off to the side and we will like do that at a certain point. Okay, yesterday, and there's a bag of material. Again, they shall be distributed at a key moment. This is a scheduled event that has certain beats that we hit and it's like a whole ceremony.
Okay.
Woo! First of all, we ended, I don't remember where we ended exactly yesterday. We were talking about, good, that's what I thought, man. We were talking about the average value of f on the interval AB. And, okay, I don't remember exactly like how far we got into this conversation, but it was something like this. We had some function, and maybe it looks like that or whatever, and we want to know how big is this function on average, and we had this whole conversation where we sort of thought of this maybe as like temperature versus time, say, and I think this was the class, we had a whole conversation about this, right, where you can't just take the average of the beginning temperature and the end temperature, because that doesn't capture how the whole day went. Nor can you take the maximum temperature, the minimum temperature, because that doesn't really capture the average temperature. What you really want to do is like sample the function. In fact, that's exactly what we did. So we partitioned the interval into subintervals. We took a sample point from each subinterval, and we added them all up, yeah? And what we ended up with is this like f of x1 star. This is going to be slightly repetitive, but I think we should get back in it. And you add up all these values of the function, and you divide by the number of sample points that you took. Not vigorously, if you're like, yeah. And if you take the limit as n goes to infinity, then that should give you the average value. Period 4 people, we're like, these guys are like 8 minutes behind, so something's going to be a repeat. Then we said that this appears if you take the sum from I equals 1 to n to be like a Riemann sum. But we had this whole conversation, right, that it's not actually a Riemann sum. Did we have this whole conversation?
Yes.
Yes, it superficially appears to be one, but no, actually, man, the Riemann sum is not just a sum that is pretty. It's a sum that has a very specific property, that the widths of the intervals and da-da-da-da. So then we said, okay, if I multiply the top and bottom by b minus a, then I sort of like collect this b minus a over n now is the width of each subinterval, and then I can pull one of the 1 over b minus a's out. And so we get 1 over b minus a times the limit as n goes to infinity of the sum from I equals 1 to n of the f of x sub I star b minus a over n. And the reason to put in effort to rewrite this as a Riemann sum is that now we can sort of invoke the definition of integral to say that in fact the average value of a function is 1 over b minus a times the integral from a to b of f. Okay, and I apologize if I know almost everything I said so far is a repeat. I don't remember if I said the following, that this is quite remarkable, I think, because what we have done is we have started with a problem, how big is a function on average, and we have arrived at our answer, and our answer is it's this integral divided by b minus a. Maybe I said this yesterday and maybe I didn't, that this is, one reason why this is remarkable is that if you think that integration is a solution to the area problem, you're like basically right, but it's not quite, or rather it's not so simple. If someone were to ask you, like say your parents maybe who don't know math or maybe knew some and forgot, what is integration anyway? What would be and you only wanted to talk to them for 10 seconds, you might say something like, yeah, it's like just like the area under a curve. That is not wrong, but it's also not the full story. Because this problem, at least on the face of it, has nothing to do with area at all. Do you appreciate this? Right? This is a problem that just started with trying to find the average value of a function, and we've ended with our answer, which is an integral. What this shows, I think, is that integration is more general than just finding the area into the curve. It is a sort of a general process which applies anytime you're adding up an infinite number of infinitely small things. And the infinitely small things that we're adding up here is sort of like the weighted contribution of any one y value or something like that is what's sort of being added, an infinite number of those. Okay, what I think we also did yesterday was to say, all right, this integral is like a number, so this whole thing is going to be a number divided by the width of this interval. And if we give this some name, what I called yesterday, a, whew, then what is really going on here is that we have now this number. And this number represents how big this function is on average. Oh, by the way, this was the class where several people, I don't remember who they were exactly, but Michio and a couple of others, just kind of like guessed by intuition that this was the average value of the function anyway. And that sort of just feels right, because you kind of like take all the, and I just said a second ago that this doesn't have anything to do with the area under the curve. It's not that it has nothing to do with it, it's just that it's not obviously about the area under the curve. But we may interpret it now as a problem about areas, because any integral problem can be sort of reinterpreted as being something about area. And what this sort of says is, hey, how big is this function on average? Kind of like asks the question like, how much like stuff is there under this curve, like on average or something? And what we have really discovered, this number a, is like the height of a line. Did I draw this line yesterday?
Yeah.
Does that look about right?
Yeah. No.
It could be a little better, but it's good enough. What we have here is this rectangle. And this rectangle has a certain area. And the claim we're sort of making here is that the area under this curve is equal to the area or the area inside this rectangle. And that's kind of another way of interpreting what average value sort of means. And that becomes, is everyone kind of with me? Right? Because what do? To get A, you take all the area under the curve, and then you divide by the width, which sort of like, what you get is like this height. And in fact, if you, though this is the definition of average value, which you'll find in like textbooks and stuff, it's perhaps helpful to like multiply both sides by b minus a. And when you multiply both sides by b minus a, what you get is like this statement, which says, yeah man, the area under the curve, all this green stuff, is like equal to the area of the red rectangle. Okay, so another way of interpreting, okay, I think, are we good?
Yeah.
Well, that's where the bell rang?
Yeah.
Yeah, okay. So, what I would now like to state is this very important theorem, which is in some ways sort of obvious. And it is called the mean value theorem for integrals. And all the mean value for theorem for integrals says is that not only does every function have an average value, but there exists some special point on the interval AB such that the function's value at that point is the average value. And so in this case, it looks like this point is like right here. Okay, so every function obtained on every interval, its average value. And so, okay, so if f is continuous, on the interval AB, blah, 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 then the mean value theorem for integrals says there exists a point C on the interval AB such that at that point C, the value of the function is the average value of the function, which is 1 over b minus a times the integral from a to b. Okay. Cool. In some ways, this is really clear, especially if you look at the picture. Surely, somewhere, the function will have to have this value. Oh, did I already say the things about the mountains and the ice sculptures and all this crap, or no?
Yeah.
Yeah. Yeah. If you have like one more way to think about average value is if you have like a sort of like a mountain range and you want to know like how big is this mountain range on average? What is the average height of this mountain? Then you can think of like erosion happening over like, whatever million years or whatever, and then when eventually you just get like flat. And whatever the height is of all the like dust after all the erosion happens is like how much mountain there was. It's how big the mountain was on average, yeah? Or if you take an ice sculpture, suppose you're having like a wild FTC day party and you have a whole ice sculpture, one day it'll happen, and then you want to know, hey, how tall is this ice sculpture on average? Then what you could do is you could just let the entire ice sculpture melt in some sort of container, right? And then, okay, then you like refreeze it, and what you would get is like a block, right? And so that we ignore that whole density problem, right? Because we refreeze it, and then whatever the height is of your rectangular block after the ice sculpture melted and then refroze was like sort of how much ice sculpture you had, so to speak, like in total. Follow? Whew, okay. All this says is that somewhere the function equals its average value. Okay, we're going to prove this because it's really important. Let's do it. Well, first I'll start with this very obvious fact that f is somewhere between. Oh, I should say let little m be the minimum of f on this interval AB, and let big M be the maximum of f on the interval AB. And that's slightly wrong what I just wrote. What I really wanted to say was the x-coordinate of the minimum. So let m be the x-coordinate, I guess it really doesn't matter, but too late. The x-coordinate of the minimum of f on AB, because that's how we used this in the past. And let m be the x-coordinate of the maximum. Okay. And so now I'll just sort of state the obvious, which is that the value of the function at any given point is somewhere between the minimum value and the maximum value. Cool. Okay. Now I shall employ this lemma, which we proved, I guess it must have been yesterday, which is that if you have if one function is bigger than another, then when you take the integral of the bigger one is bigger than the integral of the smaller one, right? Okay, so in other words, I'm just going to integrate all three sides of this inequality, and that's like legit. So I get the integral from a to b of f of little m, and the integral from a to b of f, and the integral from a to b of f of big M. Okay. But f of little m is just a y value, right? It's just the smallest y value of the function. So this is in fact a constant. This is a constant as well. And so what happens when I integrate this constant?
F of mx plus c.
I kind of know what you're talking about, but this is like an integral, right? So we're going to get, so when you integrate a constant function, what do you get? F of little m. Is everyone, yeah, right. Let's just picture the rectangle or just apply the previously grouped integral property. Okay, and here we go, integral from a to b of f of 6. And here, when I integrate, this is just a number. So when I integrate from a to b, this number, what I get is like a sort of a rectangle whose height is that number, whose width is b minus n. Okay, this is sort of like a lot of kind of technical writing. Let's draw a picture which illustrates what's going on. And the picture is going to make this thing that I just wrote like extremely obvious, bordering on like almost silly. So here's A, here's B. I'm going to try to draw the same function 3 times. And period 4, this is kind of like where we stopped ish, right? Or we did a little bit more. Anyone watching at home, but we started doing a bad job towards the end. Okay. Whew. So, this in the middle is the integral from a to b of f. So that's just this like red area or whatever. Okay, but then what is this? Well, like where does this function obtain its minimum? It appears to be happening like right here at this point, like little m, right? And so therefore that is the y value f of little m. And so that picture is just this height. And so what we're saying, this piece of sort of algebra is represented by this sort of small rectangle here. And then, of course, where the function is biggest is up here when x equals big M. So that's f of like big M. And so what we get is on the right hand, the rightmost inequality is just this thing. Okay, so like, you know, if you finding all this kind of like annoying, you can just look at this picture, which is just sort of obviously true, right? But I have proved that it is true via these previously proved integral properties. Okay. Good. I really wanted this inequality to be true because the overall thing I'm trying to show is that somewhere f of c equals the average value. All right, so we need to do one small little like kind of algebra math move now. That should seem like relatively obvious. Division. Yeah. She says then just divide by b minus a for the simple reason that I want to talk about this thing, which is 1 over b minus a times the integral. So let's just divide all three sides of this inequality by b minus a. And what we get is that f of little m is 1 over b minus a times the integral from a to b of f. And that is less than f of big M. Okay, and this just about does it. What we have now in the middle there on the bottom is the average value of the function, and what we've now shown is, okay, big surprise, that the average value of the function is some number in between wherever the function is minimum and wherever the function is maximum. Okay, well, going back to the picture, if this is little m, where my function is minimum, and this is big M, where my function is maximum, up here is f of big M, this is f of little m, then looking at this middle picture, why must my function at some point be that number in the middle? Because it's continuous, and that's like one of those things, right? If the function is down here, and then a little bit later it's up here, it must be every point in between. That is called the intermediate value. Yeah. And so we simply apply the intermediate value theorem to the function f on the interval little m big M, I guess. And what does the intermediate value theorem say? It says that if you give me any number in between f of little m and f of big M, well, here's one, then there must exist a c on the interval little m big M, such that f of c equals that intermediate value, 1 over b minus a times the integral from a to b. Okay. Whew. All right. Mean value theorem for integrals proved. In period 4, we did all this, but sort of not as well. Okay. What does it all mean? We can prove it, but let's just like talk about it, what it means. What is an interpretation of this? What is our, maybe we go back over here for a second, and maybe we don't talk about temperature and time anymore, because who cares about temperature? What's the normal functions that we're always like integrating or whatever? Probably like some kind of velocity versus time curve or something like that. So, whoa. Well, especially looking at sort of this line, maybe, well, either one, right? This says that if you have some velocity function, then somewhere on that interval, my velocity function is like average or something, and there's a point on that interval where I'm going the average velocity. That's one way of putting it. Another way of putting it is that there's some point C where the speed I'm going at that point is the speed that if I was going at that speed for the entire interval, I would get a bunch of change I would get a bunch of distance traveled, and that distance traveled would be the same as the distance that I actually traveled going this variable speed. Hold on, I said that kind of weird and backwards, right? Let f be my velocity function now. We know that the area of the green is like the total distance traveled, right? But if the area of the green is the total distance traveled, and the area of the red is like the total distance traveled for someone going at a constant velocity. In other words, there's some constant velocity at which if I just went that velocity the whole time, I would cover the same distance traveled. Does that sentence sound eerily familiar to you?
Sounds like the
It's like the
value
race
theorem for just
It sounds freaking exactly like the other mean value theorem. Notice that I talked about the other mean value theorem as being, as sort of saying that on every interval there's some representative point. Okay, just leave it on like the ground something. All right, so here's what we have. Let's recap. We have the mean value theorem. No one, let's just call it for differentiation, but no one calls it that. This is the original mean value theorem. Differentiation. And then we have the mean value theorem for integration, this new thing. And let's see what these two things say, and let's just kind of talk it all out and remember. Okay. The mean value theorem for differentiation can be understood in many different ways. One of the ways that we understood it was geometrically, and I think it's like a popular way of thinking about the mean value theorem is to say that if you have some function on some interval, then there is always a point on the interval at which the slope of the tangent line is equal to the slope of the secant line. Okay, so you take the slope of the secant line between the 2 points of any interval, and there's some special point where these two guys are parallel. Okay, that's perfectly correct. Okay, so maybe just there it is. All right, great. The mean value theorem for integration says something seemingly totally different. It says if you have some function and you want to find the area underneath it, then you can do so, and then there's some point at which the function obtains its average value. So, okay, make this hard for myself. Let's see. Sort of a fail. It's fine. There's some point at which the function obtains its average value, and so the average value of the function is like this guy, and then this is like that, or whatever. Okay, so if you just kind of like look at what the mean value theorem for differentiation and the mean value theorem for integration are saying, then they're both sort of like asserting the existence of this special point. And one seems to be about tangent lines and secant lines being parallel, and one seems to be about rectangles, and they don't seem to, seem to sound kind of similar, but don't really have anything to do with each other. But wait, if you try to extract meaning from the mean value theorems, which I recommend doing, then suddenly something very eerie happens. After all, I encouraged you back in March to think about the mean value theorem like this. You have some position versus time curve. And we know that in a position versus time curve, the slope of the secant line can be interpreted as the average velocity over that time interval. And what we said was, for some, have I done this right? Yeah. And the slope of the tangent line to the curve at a particular point is like the instantaneous velocity. And what we said is, back in March, that there's some special point C, which is representative somehow of the function on that interval. And the big takeaway here is the instantaneous velocity that we are moving at that second is the velocity that could have been going over the entire interval to achieve the same change, right? If the speed I was going at that moment, remember the whole story with me running the half marathon and there's the pacer, then it means at one moment I was running at the speed which I should have been running at a constant for the entire time to finish the race at the same time. What does this say? Well, here, it is most natural to think of this as a velocity versus time curve. And now, the green is the distance traveled, going this variable velocity. What does the mean value theorem for integrals say? It says that there's some special representative point C. And what's special about this representative point C? Well, at that moment C, the velocity I'm going is the velocity I could have been going the entire interval to achieve the exact same distance. And if you were closing your eyes during the last 3 minutes, you almost wouldn't know which one I was talking about. They're both seemingly saying the exact same thing. is very mysterious. There appears to be something really deep going on here, and I am starting to suspect that there is a deep connection between differentiation and integration. Let's get the party hats on. Okay, we're going to do an extremely efficient 2-minute operation called everyone gets a party hat and everyone gets all the food they're going to get. So if you brought food, open it up. If you have food, jump up and down and wave your arms. People descend on the food. Not sure if there's enough for everyone. Everyone get a party hat. They're extremely flimsy and half-broken, crappy party hats. Never mind.
Hey, you want to go to the vending machine? Like, we got 2 minutes, right? That's one of the good ones, bro.
That's just not the same.
Party hat that will go in your head.
There's more food here? Oh man, I need
Other plates? Where are the plates? FTC go in here. Good.
I don't want to take
Go.
There's like 8
Wait. Good, wait, get everyone get back to your seat in. 20, 19, 18, 17, 16, 15. Something you're going to give everyone one of these. Colin, can you pick up the camera and move it over there and kind of like next to Neanderthal?
I listened to you.
Could you take this and stuff? I don't have a free hand.
Where you are right now? Woo! All right. Good, Josie, thank you. All right, so, dude, it's time for like the real talk. There is this thing called differentiation, and there is this thing called integration. And okay, depending on how much mental energy you put into this, or various little small comments like let's slip throughout, you may be starting to feel that these have something to do with each other. In fact, it's the kind of thing, what I'm about to tell you is the kind of thing that you might find extremely surprising, shocking even, or you might find to be totally obvious. Or you might find it shocking and surprising, and then by like tomorrow, you might think it's totally obvious. So that's pretty interesting. Someone erase that backboard. Let's first notice that on the surface, these two problems have absolutely nothing to do with each other, especially if you focus on the geometry of the situation, which is what people often do. What is differentiation? It is the solution to the tangent line problem. What is the tangent line problem? The tangent line problem says, given some curve, find the slope of the tangent line to the curve. And how did we solve the tangent line problem? We took a particular point A on the curve that we were interested in. We picked another point X, which was a little bit bigger. We drew the secant line, and then we moved those 2 points infinitely close together, and we eventually got the tangent line. All of this is like just kind of like a review. And we defined / discovered that the derivative of a function at a certain point is like the limit as x approaches a of f of x minus f of a over x minus a. Great, tangent line problem solved. On the other hand, integration, we came out from a completely different direction because we posed it as a totally, seemingly unrelated problem. It's the problem of finding the area under a curve. How do you find the area under a curve? You approximate it with rectangles, and eventually we got to the point where we realized, okay, to find the area under this curve, I need to take an interval from A to B, I need to partition it up into subintervals, then I need to take, sample points on the subintervals, and, blah, 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 we get the area under the curve. And thus, the integral from A to B of some function on some particular interval, also a number, is like the limit as n approaches infinity of the corresponding Riemann sum. Okay. when you say it like that, integration is the solution to the area problem, differentiation is the solution to the tangent line problem, do you agree that they don't appear to be related at all, right?
Yep.
Okay, but when you start interpreting what they mean, it is and this is what some people have already been sort of noticing over the past couple of weeks. What was the point of differentiation after all? We have a position versus time curve. And the whole entire reason why we first posed the tangent line problem is because we wanted to know the instantaneous rate of change. And we interpreted the slope of this red line as being that instantaneous rate of change. In other words, the velocity. So if you take the derivative of a position function, you get a velocity. But the reason why we wanted to solve the area problem is because we had a function with some variable velocity, and we wanted to find the total distance traveled. And in fact, that's what the integral will give you, the total distance traveled. So somehow, the derivative of a position function is velocity, and the integral of a velocity function is a change in position. It appears as if differentiation and integration are somehow like inverse processes. And in fact, this is true. All right. Whoa. Without further ado, things are getting serious now. Get this worksheet called Accumulator Functions, and basically just kind of like begin immediately. What's happening here is you have a picture. This picture is a graph. This graph is called f. A function g is being defined, and this function g is an integral, sort of. It's an integral whose lower limit of integration is -4, and whose upper limit of integration depends on the input. Follow? So what you're inputting to this function is sort of how far out do I integrate. Good? Okay, go help each other, take 2 minutes and like do this. Top half of the page. Or keep going if you have time.
We just spent like 2 hours listening to 103 songs.
Also, someone like Sam or someone maybe can you like camera or video or whatever.
That's how it be.
I think this is add up. Yes.
So these are called accumulator functions because what's happening is as x is changing, we're like accumulating area. In my